Alright, for this first problem here, we're of course going to start with our chart listing all the variables. So reading through the problem, we know that we're initially walking at a speed of 2 meters per second, and this cat here is going to speed up to a speed of 9 meters per second. So those are going to be our initial and final velocities, and that change occurs over a displacement of 4.3 meters. So that is our delta x. We're then going to go ahead and set up our first equation here, which is going to be VF squared equals VI squared plus 2A delta x. So we have 9 squared equals 2 squared plus 2 times A times 4.3. So it ends up being 81 equals 4 plus 8.6a. And that's just because when these three things are multiplied together, we can multiply them in any order. So I'm just going to multiply the 2 and the 4.3 to get 8.6. I go ahead and subtract the 4 to get 77 equals 8.6a. Dividing by 8.6, I get my acceleration here is 8.95 meters per second squared. Solving for my time, I'm just going to set up a different equation here. We have a few options here, but the one that I'm going to use is the VF is equal to VI plus AT equation. So I can say 9 is equal to 2 plus that acceleration I just found, which was 8.95 times t. So 7 is going to be equal to 8.95t, and I divide by 8.95 to get a time here of 0.78 seconds. Alright, moving on to the next one, starting with my chart once again. With this Tower of Terror one, what we're going to think about is, first of all, the people are being dropped. That's going to indicate that our initial velocity is 0 here. We know the riders are in free fall. That tells us that our acceleration is 9.8 meters per second squared, because that's always the acceleration while in free fall. And we know we're in free fall for 2.1 seconds. So this is just a case of an object starting up here at some initial velocity of 0 and just falling. Okay, so we don't have to worry about any of that symmetrical, doubling the time at the peak, any of that stuff. This is just an object starting at rest and dropping for 2.1 seconds, and we want to find this displacement here. So the equation that I'm going to use is the delta x is equal to VIT plus 1/2 AT squared equation. Alright, so we sub in the things we know. We're solving for delta x, of course. Our initial velocity is 0 times that 2.1, which means that entire term there just goes away, plus 1/2 times negative 9.8 times 2.1 squared. Only the 2.1 is squared. Be careful about that. So we go ahead and do our math here, and we end up getting a delta x of negative 21.6 meters. For the answer, though, if you would put positive 21.6, because it does say how far do they fall, and it's kind of redundant to say that they fall a negative distance of 21.6 meters. So either one would have been acceptable. It's a displacement of negative 21.6, or they fall 21.6 meters. Alright, for this next one, we have Ichabod throwing a pumpkin straight up in the air, and it's in the air for a total time of 1.2 seconds before it returns to the same height. Two things I'm going to do here. Number one, I'm first going to fill in my acceleration, of course. We know that no matter what part of this we're thinking about, that acceleration is going to be negative 9.8. And the second thing I'm going to do is I'm going to draw that diagram showing the object going up to the peak and then falling back down. Something like that there. So the things that I know at the peak, my velocity is 0. I know down here when it returns, my time is 1.2 seconds. Okay, that is the total time it's in air for. So that's down here. I know my displacement down here will be 0, and I know that my time at the peak here will be 0.6 seconds. Okay, so I do have two options. I can either think about the entire time the object's in the air going up and coming back down, or I can just focus on this going up period. I'm going to focus just on the going up period, and part of that is because I See, in the next problem, it's asking for the maximum height, which I know is also going to happen at the peak, but you certainly could use the two concepts from the end to finish this. So since I'm just thinking about going up to the peak, the two concepts I'm going to use is that my final velocity is 0 and my time is 0.6 seconds. And now I can go ahead and use that to solve for my initial velocity. So I'm going to say Vf equals Vi plus At. 0 is going to be equal to Vi plus negative 9.8 multiplied by our time here, which is 0.6 seconds. And that means that my initial velocity, well, it's going to be Vi minus 5.88. So my initial velocity here is going to end up being 5.88 meters per second. Moving on to finding the maximum height. I'm looking for delta x here. There are a few ways of doing this. I'm just going to use I think the easiest one is delta x equals 1/2 Vf plus Vi multiplied by t, but certainly the other equations would work. So I'm going to say that my delta x here is going to be equal to 1/2 times 0 plus 5.88 multiplied by 0.6. So I get that delta x here is 1.76 meters. For the last one, we need to do a quick sketch of the velocity versus time graph. We know that there is some initial velocity, so I know that in the very beginning I'm going to have some point up here that I'm starting with. I also know that my acceleration is going to be negative, and it's going to slow down initially and then speed back up in the negative direction. And so ultimately my graph here is going to look like that, just a line with a negative slope. This first part is showing initially how it has a positive velocity but slowing down to 0 as it rises up to the peak. Once it hits the peak, then it speeds back up in the negative direction as it falls back to the ground. Moving on to number 4 here, we have another free fall problem. This time it's toilet paper flying up in the air with some initial velocity of 16 meters per second and getting stuck in a tree. So first thing I'm going to do is I'm going to put in my acceleration as negative 9.8 meters per second squared, because I know that once again it's in free fall. And I'm going to once again draw the sketch of this off to the side here, so it goes up to the peak and then it falls back down, but it ends up landing here 6 meters above that point from which it started. This is not symmetrical. We still can say our velocity is 0 at the peak, but a lot of those other concepts go away. What I can say though is I can say my displacement is 6 meters because that's where I end up, and I also know that my initial velocity is at 16. And that actually ends up being enough information. Now I know some folks found the time to the peak and then from the peak went back down, and that's okay, but you don't actually have to do that. We can do this all in one motion here. We can think about the whole time it's in the air using this setup that we have here, because that is the overall displacement, that is the initial velocity, and of course the entire time our acceleration is negative 9.8 meters per second squared. All right, so we're going to go ahead then and set up, first I'm going to set up my Vf squared equals Vi squared plus 2a delta x. I ultimately am looking for my time here. However, I know that this is a setup, knowing my initial velocity, displacement, acceleration, that will lead to a quadratic. So I'm going to use that quadratic trick, solve for that final velocity first using my Vf squared equation, and then I'll go ahead and solve for my time once I know what my final velocity is. Alright, so I go ahead and put in the things that I know there, and I end up getting that Vf squared is going to be equal to 138.4, and that means that Vf is going to be plus or minus 11.76 meters per second. Okay, and it's very important that we put in that plus or minus. We have to always do that sign check here whenever we do the quadratic trick. Taking the square root of Vf squared, we get two answers. And in this case, the answer ends up being negative because we're thinking about this point right here, when the object is traveling down. So that means we are going to take that negative, and now we can use VF equals VI plus AT. So negative 11.76 is equal to 16 plus negative 9.8 times t, which means we end up with negative 27.676 is equal to negative 9.8t, and so my time here ends up being 2.83 seconds. And that is my final answer. That's the overall time this object is in the air. All right, let's go ahead and do number 5 here. Number 5 has a really important feature right off the bat that you need to recognize, and that is that we have a situation where this police officer is accelerating at a rate of 3.5 meters per second, and then after that maintaining a constant speed. And so that immediately indicates to us that we need not just one, but two setups here, one for the period of time while we're speeding up, one for the period of time where we're going at a constant. So I'm going to fill in what I know for each one. So I know that while speeding up, that distance is 10 meters. We're starting from rest here, so the initial velocity will be 0. And I know that my acceleration is 3.5 meters per second squared. So I actually have a lot of stuff with that one. For the constant, I know that because it's a constant, my acceleration is 0. I know that the distance for the constant must be 50 meters. And the reason for that is the total distance is 60, okay? If we take away the 10 initially, that means that it's going to be 50 meters remaining. The other thing that I know, and this is going to be important a little bit later, is that whatever final velocity I have here, that's going to become that constant velocity. So however fast I'm traveling at the end of that speeding up portion, that's going to become my initial velocity at the beginning of my constant portion. So I'm going to start by working with my speeding up portion. Ultimately, we're trying to find the time for each one. So we'll start by finding the time for the speeding up portion. So I can say delta x equals VIT plus 1/2 AT squared, based off of what I know so far for the speeding up. So I can say 10 is going to be equal to 0 times t, which means that that entire term there is just going to go away, plus 1/2 3.5 t squared. All right. So I end up getting 10 is equal to 1.75 t squared. Dividing by 1.75, I get 5.71 is going to be equal to t squared, so that means my time for the speeding up portion is going to be equal to 2.39 seconds. Knowing that I also want to find my final velocity, again because of this link that I just talked about up here, I'm going to go ahead and solve for that final velocity. A few ways we could do that, but I'm just going to say VF equals VI plus AT. So VF is going to be equal to 0 plus my acceleration, which is 3.5, times 2.39 seconds. So I get a final velocity there of 8.37 meters per second. Now that I know that final velocity, which again becomes my initial velocity here, I can go ahead and solve for my constant. I also can technically say that my final velocity here for the constant is 8.37, because if I'm traveling at a constant velocity, it means that it's not changing, so I can fill in that 8.37 for both. I'm going to once ahead go to my delta x equals VIT plus 1/2 AT squared. I know actually that that entire second term just goes away because my acceleration is 0. So what I'm left with is just 50, which is my displacement, equals 8.37 t. And so I end up getting that my time here for that second portion is going to end up being 5.98 seconds. Keep in mind that whenever you're doing a constant velocity situation with zero acceleration, you have to use one of the delta x equations, either the one that I used here or the delta x equals 1/2 vf plus vi multiplied by t. Now that I have both of my times, what I'm going to do is I'm simply going to combine them. So I'm going to take this time and put them together. And when I add those two times together, I end up getting a total time of 8.37 seconds. All right, moving on to this next one. Once again, this one requires two steps. The reason for that is we have two objects here, a goblin and a ghoul. So we're going to make a setup for each one. So we know they're running a 100-meter race. That means the displacement for each one of these objects is going to be 100 meters. So I can go ahead and fill that in for both. The goblin starts from rest and accelerates at this rate here. So that tells us that for the goblin, the initial velocity is going to be 0, and our acceleration is going to be 0.75 meters per second squared. The ghoul, on the other hand, runs at a constant speed the entire time, which means we know that for the ghoul, the acceleration is going to be 0. We don't know what that speed is yet, but we do know that it is a constant speed. So now we can go ahead. Oh, the one other thing that's important is this last line here about the goblin ends up finishing the race in 1 second less than the ghoul. That's going to give us a link between our times. We don't have an exact value yet. We're going to have to solve for the stuff about the goblin first, but that's something we want to keep in mind. So I'm going to start with the goblin because we know more information there. I'm going to use the delta x is equal to VIT plus 1/2 AT squared equation. Since that initial velocity is 0, that means this entire term just goes away. 0 multiplied by any time is going to be 0. And so I can say 100 is equal to 1/2 times my acceleration, which is 0.75, times t squared. So 100 is going to be equal to 0.375 t squared. Dividing both sides by that 0.375, I get 266.7 is going to be equal to t squared. And then when I take the square root of both sides, I end up here with a time of 16.33 seconds. No need to do a plus or minus here because it is a time, so it has to be positive. Now I'm going to use this line here that the goblin ends up finishing 1 second less than the ghoul. So the goblin is winning the race. The goblin's finishing faster. So if the goblin finishes in 16.33, the ghoul must have taken a time here of 17.33 seconds to finish the race. That would allow the goblin to finish in 1 second less than the ghoul. Now that we know all this stuff about the ghoul, we can go ahead and set up that same equation for the ghoul now, but we're going to be looking for the velocity of the ghoul, right? What is the speed? In this case, the speed really is just the velocity minus the direction. So we're going to be looking for the velocity of the ghoul here. So we're going to go ahead and use that delta x equals VIT plus 1/2 AT squared equation. Since my acceleration here is 0, I know that this entire term goes away, so we can just cancel it out. And then we're going to fill in the things that we know. So we know our displacement is 100. That's going to be equal to our initial velocity multiplied by our time of 17.33. Keep in mind that that initial velocity will also be our final velocity because we're traveling at a constant speed here. Okay, so it's going to be the same. So I solve for that initial velocity, and I get 5.77 meters per second. That is the constant velocity that the ghoul travels at. That would be both the initial and the final velocity of the ghoul. So that ultimately is my final answer. Alright, let's move on to these vector problems here. So we're starting with this initial vector, 20 meters, and that's going up and to the left. So that means that my x vector is going to be going left, my y vector is going to be going up. We want to first draw those vectors, and then we're going to go ahead and solve for them. So there's my x side, and there is my y side. Think about the sides of the triangle that we have. My x side ends up being the adjacent side. That's going to be important for solving for this. And my y ends up being the opposite side. Now that I know that, I'm going to go ahead and solve for both x and y. We'll start with x here. And so since x is my adjacent side, I know I'm going to be using cosine. It's going to be the magnitude times the cosine of the angle, so 20 cosine 38. And I end up getting that my x side is going to be equal to 15.76. My units are going to be meters, and the reason for that is those were the units of the overall magnitude. Those were meters as well, so my x component has units of meters too. Moving on to my y side, that is my opposite side, and so it's going to be 20 times sine of the angle. That's always going to be true for the opposite side. So for y, I end up getting 12.31. That's going to be meters as well for the units. I'm now going to go ahead and fill in that final answer, including the direction. So the x is going to be 15.76 meters, and that x component is going west, as we see up here. The direction of it is to the left. The y component is going to be 12.31 meters, and that's going to be going north for the same reason. We see that that y component is going up. Alright, moving on to my other vector here, this 40 meters at an angle of 15 degrees west of south. So this one we're going to go ahead and have to draw. So maybe you draw that northeast, southwest little coordinate system there off to the side if that's beneficial to you. Maybe you're at the point where you can just draw it. But what I'm going to start with is just think about that angle, 15 degrees west of south. That means we're starting with this south direction here and going west. So I know that vector is going to be going down and to the left here in that southwest direction. And because of how this is worded, because it's 15 degrees west of south, that tells me that this angle in here is going to be my 15 degrees. I can now go ahead and draw my components. So there is my y component going down. There's my x component going to the left. And in this case, it's actually flipped from the other one. I know that my y component is going to be my adjacent, and my x component is going to be my opposite side here. Now that I have that, I can go ahead and fill in or solve for both the x and the y. We'll start with the x side once again. Since the x is now the opposite, it's going to be 40 sine of our angle of 15 here. So for that x side, we end up getting 10.35. The units are going to be the same as the overall, so those units are going to be meters per second. For my y, I'm going to end up getting y is equal to 40 cosine of 15, so that y side ends up being 38.64 meters per second once again. Filling them in with direction, in the horizontal direction, that 10.35 meters per second is going west because it's going to the left, and the 38.64 meters per second is going to be going south. Moving on to my final problem here, I have two components. I'm going to put them back together to get the overall. So first going to just draw out the two components. So my first one is this 30 newtons east. So I'm going to draw a vector going east. It's going to have a magnitude of 30 newtons. Keep in mind that newtons is the unit, not the direction. And then from there, tip to tail, we're going to go 45 newtons south. So that's going to be a vector that looks like that. We see there how that tip to tail is lined up. So that means that overall my vector is going to be down and to the right here. So we're going to solve for the hypotenuse and also for this angle here. When it says solve for the direction, that's really what it's talking about. Is it means find the angle that that vector makes. Give the direction including the angle. So in order to get the hypotenuse, I'm going to say a squared plus b squared equals c squared. So 30 squared plus 45 squared equals c squared. That means that c is going to be 2,925. And when I solve for that, taking the square root, I end up getting that my hypotenuse here is 54.1 newtons. All right, so that is the magnitude of that vector. I'm now going to go ahead and solve for the direction. Like I said, that really means find that angle. So in order to get that direction, what I'm going to say is, I'm going to say tangent of that angle is equal to the opposite over the adjacent. That's just the definition of tangent. This 45 is going to be my opposite side here. This 30 is going to be my adjacent side, the side touching the angle. And so I can say tangent of theta is going to be equal to 45 over 30. All right. I'm now going to take the inverse tangent of both sides. That's going to get theta by itself. So what I end up getting now is that theta is equal to the inverse tangent of 45 over 30. So I find that my angle in this case is going to be 56.3 degrees. I'm now going to put in that final answer. So magnitude and direction. My magnitude is going to be that 54.1 newtons. My direction is going to be 56.3 degrees. I do need to specify the direction though, what of what. So if I look up here at my vector, that angle is measured relative to the east direction, and from that east direction we go south, and that means that it ends up being south of the east direction, 56.3 degrees south of east. If you had drawn your components differently, if you went down first, okay, and then you went east, and you drew your vector like that and found this angle here, that's perfectly okay. You just would have gotten an answer of 33.7 degrees, and then it would have been east of south instead. So that one's acceptable. You don't need to list both, but there is another possible answer for the direction.